Well, he's back. Last year he gave me an award, patted me on the back, and sent me on my way. Unfortunately, Richard made a mistake. He forgot to sweep up the breadcrumbs. So, anyway. So about a year ago, I was asked to chair a new ad hoc group. This particular ad hoc group actually started out as mobile broadcast services, but we realized that it's more than just mobile, it's core. So this particular ad hoc group is not creating any normative documents, but rather we're looking at the needs of broadcasters. How do you take some of the things you've learned so far, and we'll learn later this afternoon, and use it to your advantage? And so we have done a few things within 32-4. We've created a CN bitrate calculator, which I'll show you in a moment. We've developed a use case calculator, which I'll also show you shortly after that. And then we're in the process of developing example coverage maps, and I'm going to show you a few of the things that we've done so far. I decided to bring back this particular chart. You've seen it a few times today already, but simply to illustrate that, if I can click through this, you know, with A53 you had one operating point. And as you've learned now, we've got oodles of operating points, dozens of operating points. So frankly, how do you decide where to set the knob, or the knobs, several of them? So Tim Laud and Wayne Brettel produced this, Zenith produced this CN calculator sheet, and then Jay Lee and Sagnat Park added LDM to it to enhance it for LDM applications. And basically, it's a calculator, it's a work in progress, but it's a calculator sheet where you pick all of the things on the, shown on the right side, and plug in the numbers, and out pops some answers. And so you see, you enter those things, and out pops your answer. So I brought in a close-up of the output sheet, and this happens to be a two-layer LDM configuration, showing you what under the specific configurations that were entered, what would be the payload, what would be the threshold AWGN, and also, more importantly, what would be the threshold at relay. It also shows you what the top-end Doppler speeds would be for each of the two layers. So this is a sheet that we would expect people would use. And the way I really look at it is you enter some transmitter settings and out pops some expected performance. But really, you're going to have to loop around and continually update this and run around until you get to a configuration that you think you want. And then you move on to the next thing. The next thing is a coverage use case spreadsheet, which was developed by Kent Walker of Qualcomm. This is a very elaborate sheet. This is actually only one sheet of a large workbook, and it's obviously an eye chart, so I blew up a few of the important things. And basically, you would enter the green areas. The blue areas are pre-entered with data, either from theory or from actual experience, and then some of the results would come out in terms of the calculated numbers. Now, included in this workbook, will be available, are the upper and lower bands, sheets for each of the upper and lower ends of each of the three bands. Plus, there's a sheet of a large number of reference charts and use case user's guide, how to use this thing. So all of this was created, as I said, by Kent at Qualcomm and his team there, largely based on their actual experiences with media flow, which has a great similarity to what we're talking about here. So this particular use case also applies to a variety of different kinds of receivers and obviously receiver antenna configurations, as well, and not only for urban, suburban, automotive, indoor, outdoor, rooftop, and all of that. So it's a very exhaustive sheet that will be made available. So coming back to this, really what we're showing, the preceding speakers have been talking about, is that TDM can really operate anywhere along the curve with either a single physical PLP, physical layer pipe, or multiple PLPs. And with LDM, you'll be able to operate in two areas of that. So in using the tools I just showed you, you'll be able to slide up and down the curve and decide where you want to operate. So the next thing I'm going to turn to that we've been working on are maps. We want to illustrate examples of what this 3.0 system can do. And we've been using EDX and SPLAT so far. EDX, a high-end, very popular mapping tool. And then also we've been using SPLAT, which is an open source Linux base. And I have to give a big shout out to Doug Lung, who's been the bulk of the work that's been done so far. And all of the following coverage plots that I'm going to show you have been done using SPLAT with some scripted extensions written in Python that Doug created. And I also want to give out a personal shout out to Doug because he spent hours with me teaching me the fine art of Linux, Python, and SPLAT. And I'm actually in my semi-retirement having a great time creating plots at home. Anyway, we are also going to be looking at vSoft. Merrill Weiss has been doing work with EDX. As I said, Doug and I are now doing work with SPLAT. And with vSoft, Tom Hankinson and Bill Hayes are going to be working with that. So we're going to be using all of these three tools and comparing notes to see how they come out. Because frankly, these are all based on models. And models can be wrong. We think they're pretty good, but they all have their limitations. So first thing I have to do is give you a very large caveat. Following coverage plots are what the 3.0 system could do. It's not what it will do, but what it could do. I want to assure you that I've done no frequency searches, I've done no applications of the FCC, or none of that. These are simply examples about what could happen. Also, we made no interference studies to date. We've talked about doing that, but in order to do interference studies, we would have to lay out a large area of the country and figure out what are the co-channel, adjacent channel interference configurations, et cetera. So that's something that's a lot more exhaustive than we've done so far, but it's in our discussions. Also, I want to stress that all of the plots shown here have been done using Longley Rice, but we're doing it at F9590 and at not at 30 feet, but rather at 4 meters. Now, why F9590? We feel that it's a lot more realistic in terms of the output of what I'm about to show you and all the other maps that we've created in terms of mobile, pedestrian, indoor reception. The F5090 that you're all used to, that the FCC uses, is fine as a reference point, but as we've all found out in our field experiences, is not very realistic for mobile, pedestrian, or deep indoor. And then also, we're using a height of 4 meters. It's a bit of a compromise. Longley Rice doesn't work very well at very low heights, like 1.5 meters pedestrian height, but 30 feet or 9.1 meters is rooftop. And what we want to do is look at the realistic performance, or more realistic performance of the plots at a much lower height. Now, I'm going to talk about other models towards the end of my presentation, but these were all done with Longley Rice. So our project includes 4 markets. We decided to pick on 4 markets. Washington, because obviously it's the nation's capital, very highlight, spotlight. We've done the UHF. We're going to be doing VHF studies using existing sites. San Francisco, because it's a very difficult terrain, difficult in both the suburban as well as urban terrain. Atlanta, which is kind of a mid-level terrain, still has terrain, but less difficult than San Francisco. And then finally, we ask ourselves, what if we created a regional or an entire statewide SFN, single frequency network? Again, we're not doing any applications of the FCC. We've done no frequency searches. We're just asking, what would it look like if we actually did that? So here's the first plot done by Doug. This happens to be imagining what WRC, the NBC O&O here in Washington, would look like at 1 megawatt ERP on channel 36. Again, very fictitious, but we did use the actual antenna, tower location, antenna height, and the antenna pattern that WRC has right now. So this is what it would look like. And what I'm showing you here are actually JPEGs of a Google Earth presentation. What our process produces, the Splat and Python script process produces is a KMZ file, which is an overlay to anything that can handle a KML display, like Google Earth is what we've been using. But any other application that handles the keyhole markup language will work. And so we're using Google Earth because it's obviously very portable. Everybody here can download it, and you have it, and you can then create or access the overlays if you wish. The guide on the left side is in dB microvolts per meter. The very bottom is 40, 41 being at UHF, being the noise-limited contour level for the FCC's determination of your noise limited contour, and it goes all the way up past 100 dB. In these plots, I want you to think about 80 to 85 and above. 80 to 85 is kind of a good rule of thumb for good handheld, pedestrian, mobile, or deep indoor reception. You need that much level in order to get a good performance, good reception. So as you can see here in this area, which is a very wide area, I didn't include a scale, which I probably should in subsequent maps, but it's a very large area of the display of the Washington area. And you can see that certainly around the first, second, third ring suburbs of Washington, we're already at 80 dB or above. So we asked ourselves, what would happen if we added this hypothetical SFN? So we picked 4 sites. The 4 sites were picked only because there happens to be a tower, an actual tower at that location. And again, we didn't contact the tower owners, so they don't even know we've done this, except for one. I did contact, in Annapolis, I did contact the public television station. That happens to be their tower outside of Annapolis. The other 3 towers are probably carrier towers. The other 3 towers are under 100 meters. Annapolis was set at, I think, 225 meters. The 4 sites around WRC are 250 kilowatts ERP that we simply selected. So in this particular configuration, if you were a broadcaster and you're starting to think about an SFN and what would it look like, and I brought my own little thing. You can see the Christie Farms site is way down here just west of Stafford, which is quite a ways outside of the metropolitan area, but still within WRC's coverage area. If they wanted to have a good, solid mobile performance, they might want to think about either adding another SFN site in here or pulling in the Christie sites there. And similarly, the Ravens Rock is way to the west-northwest, way out there on the mountain chain. But you can see that there's some areas in here that are probably lower than you would want for good indoor or mobile performance. So you might want to either pull in the Ravens Rock or add some more. And the point here is that using some of these tools, you can start to design an SFN and figure out where it would be covered. Now, all of these 4 add-on transmitters were plotted with omnidirectional antennas. We just picked them, but in point, as Luke actually pointed out this morning, if you were designing an SFN, you would probably pick a highly directional antenna, aim it inwards, and then position it at the location you want it. And one of the things that might end up, what I've done here is done a blow-up. Actually, I just zoomed in to that previous map. So you can see this is a close-up. And there's, if you see the faint outline, this is the district diamond that we're inside. But you can see out here, all the way down south of Alexandria, up here in the Wheaton area, and you can see to the east and the west, a very large area of this is already at 80 dB or higher. So I would say that we felt comfortable that at least in this go-around, we've already gotten to a point where this is a reasonable start in terms of providing performance for indoor or mobile or pedestrian. So anyway, I'm going to move on. Now, you know, throwing energy, throwing power into your coverage area isn't actually your goal. Your goal is to cover people, and so what we ask ourselves, actually, what Doug has done is pulled in the 2010 census and mapped that to each of the cells. Actually, one of the things I forgot to mention is the previous maps and the subsequent maps were all done with using SRTM data, terrain data, 3-second data, which is about 300 feet on the side. So with Google Earth, if you had this display, you would be able to zoom right in. I can't do it here because these are solid JPEGs, but you'd be able to zoom in all the way down to the block or even closer than that and look at what you would expect the performance to be. So if you really wanted to look at your coverage area and look at what the impact is of moving SFN transmitters around, you'd be able to do that. It's a highly iterative process, but that's what you would probably do in terms of designing your SFN. So in this particular configuration, without doing any further design work, you can see the single transmitter, WRC, our hypothetical transmitter, covers at 80 dB microvolts per meter, covers 2.8 million people. By adding the other 4 transmitters, it covers almost 4.6 million people, or a 63% increase in population. Now, this is a cost benefit. You can figure out what the costs are with regard to adding the transmitters, and you can actually mitigate the costs if you work with the other broadcasters in the area and establish common SFN sites. And here you can also figure out what the benefit is. How many more people are you going to cover? Now, if you know your business and know how many more people you can cover, you can figure out, well, what's the value to me of that? So you can, using some of these tools, come up with what the cost-benefit ratio is going to be for adding this particular thing. And then again, you can go through an iterative process and refine it. So these are tools that are going to be available to all of you. A couple other maps of interest. What would be the strongest server in this particular configuration? You can see the 5 colors representing the 5 transmitters. But probably more importantly is what are the number of servers that would be covered. You can see from, especially to the north and the northeast of WRC, there's a large number of transmitters. The orange is 1 transmitter that reaches a particular receiver at that point at 80 dB microvolts per meter. But you can see where you can get to 2, 3, 4, and then if you zoomed in, you could find 5 in some of those locations. And so you're going to be in those areas saturating the market with a lot of signal and thus probably ensuring yourself of very good coverage. So then I took my turn at Linux and Splat, and I asked what would happen if we covered the entire state of Iowa. Bill Hayes shared with us it's on our little team, shared with us the transmitter data. These are the 9 full-power transmitters of Iowa Public Television modeled as an SFN. Now, IPTV is committed to covering all of the citizens of the state of Iowa, and so they actually have translators in the south and the northwest, which I'll be getting data from that and adding to this map in due course. But this is, again, modeled on channel 36, again at F9590 at 4-meter receive height. And again, if this was actually Google Earth, I would be able to zoom in and show you where I can hit that 80 dB microvolts per meter and show you where we would expect good SFN. Now, what Bill and his team would do in this particular case is if they wanted to, you can see there's a lot of empty areas in between the transmitters. They'd have to decide for themselves, well, what's the cost benefit of adding anything there, any additional transmitters? How much do I want to add? What's it going to cost, and what value is that going to bring to me? So Again, this is a tool, and again, we made no frequency searches, so this is all hypothetical, but it's something that could be conceived in the future. So I want to come back to this particular chart because it's an important point to make. Adding an SFN transmitter isn't a matter of simply filling in an area and all of that. By adding signal level, by increasing the signal density, the levels up there, you can actually move up the Shannon curve. And by moving up the Shannon curve, you're giving up a little bit of robustness, but what you're doing is adding capacity. And so by throwing more signal into the area, you can operate at a higher point on the Shannon curve if you want to, thus giving you more bits. Bits are bucks. So you can figure out, well, what's the cost of doing that? Again, what's the cost of adding that signal level? And what is the benefit to me in terms of the bits? So again, it's a cost-benefit ratio. And it's something, using these tools, you'll be able to figure that out over time. So I wanted to talk about models. Longley-Rice is an important model, number one, because the FCC uses it, and I don't know there's any plan to change at this point. There are other models, such as Hada-Davidson, which actually the use case spreadsheet that Kent provided uses that, which is more useful for urban clutter. There are other models that you've heard about, TIREM and so on. We need to use, well, not only those two models, we need to use a multiple of models to figure out exactly what our coverage is, because when you're going to start spending a lot of money, you want to make sure that you've got it right. For right now, in terms of rules of thumb, we suggest that from suburban to urban, that you think about, if you're going to use a Longley-Rice model, think about subtracting 6 to 9 dB from the Longley-Rice to yield a more realistic performance in the urban environment. So, in summary, you got, as you've seen so far, you've got many modulation settings to tailor the broadcast for your specific business, et cetera. You're going to have the opportunity through SFNs to balance robustness, payload capacity. You're going to have SFN options to be able to shape coverage and fill in the difficult areas for realistic fixed and mobile services. And we're working hard to make sure that tools are available for you to figure all of this out. Yeah. Can you change that? I think we're frozen. Oh, I see. I put in builds in there. I probably should have. Thank you. So as a now former and semi-retired, so to speak, broadcaster, I really asked myself, well, what does this mean to me? Well, it provides, the 3.0 is going to provide me the ability to receive off-air signals on handheld devices deep indoors if I design the system right. But it's also going to provide me the option of providing significant number of multicast services ranging from UHD all the way down to SD, which is still very important. But probably more important, this most important bullet to me is that it not only allows me the ability to model what I'm going to do from the start, but the whole system gives me the options of changing my business model, changing my configuration, changing my modulation, changing everything as time goes on, as my business plan changes, and thus I have the agility to react to a changing business model. If I want to change that, I have the option of changing some of the modulation parameters, and if I've designed my SFN properly, I've covered and saturated the area, and I can operate wherever I need to along that curve that you've seen several times today. So anyway, that's it for me. Any questions? Bill?
Yeah, Jim, on this, the 6 to 9 dB subtraction, that's from the 95-90 curve, correct? What was that?
Generally, yes. Yes. I'll let Kent modify that answer if he wants to. But. TR.
You mentioned these tools to be available for broadcast. How?
Good question. One thing I didn't mention. The ad hoc group, we would like to finish our, we're preparing a preliminary report that will be out by the end of summer. That's what we're saying right now, along with all the candidate standards and all that, or many of them. How it's distributed to other, to people outside of ATSC is yet to be determined, and we need to work that out with TG3 and ATSC itself. I will say that everything you've seen, all of the plots, the dozens and dozens of plots that we've done, all the Python scripts, if you really want to dig into it, all the databases, the population databases and all that, are all available to all S32-4 members now. We established a depository using Google Drive, and we provided access to that to all 32-4 members. So if you want to join 32-4, they're yours today. You know. Winston.
Yeah, thanks. Just a comment, and Winston Caldwell with Fox also. And you made these points in your presentation, but just to tie a couple aspects together is when you were showing your plots ranging from blue to red and all the colors in between, and there was this equation from 80 dB microvolt per meter to an association to indoor coverage. That's true based on a certain capacity configuration of your pipe. And of course, this service, as you stated, allows that to be more of a sliding scale, that if you wanted to make more of the red color be suitable for indoor coverage, that you could configure your system to deliver that so that it is receivable indoor. So
that's correct.
Just to make that point, that while we were looking at that, seeing blue-green is really where you get indoor coverage, well, in fact, it could be all the way out to the red part if you so wanted to limit your
if you
pipe
chose
to
very high, robust.
Lower capacity systems.
Yeah, good point. Thank you. Okay. Anyone else? All right. Thank you.